Hello everyone, my name is Fred Rispoli and I'm coming to you from Stony Brook University. In this video, we're going to study Bayes' theorem examples. So we'll go through three different examples involving Bayes' theorem. You can see the first one gives us probabilities related to HIV infection tests. The second gives probabilities related to defective refrigerators, and the third, married workers. So first we'll start with an overview of Bayes' theorem with just, let's say, two sets. So suppose we have a sample space and we could divide it up into A1 and A2. Then when calculating the probability of A1 given B, Bayes' theorem tells us that we can calculate the numerator using the probability of B given A1 times the probability of A1. This is really just an expression that we could use to calculate probability of A1 intersect B. And we could calculate the probability of B by breaking it up into two parts. The probability of B given A1 times the probability of A1 plus the probability of B given A2 times the probability of A2. And we can interpret some of this in terms of a probability tree. If we create a tree based on our division of the sample space, and this is the probability of A1, the probability of A2, right? These probabilities must add to 1. Then calculating the probability of A1 given B can be obtained by finding the product of probabilities along the path through A1 that goes to B. So that would be this path here, goes through A1 and goes to B. This is the probability of B given A1. Right? Generally, we're given this information, and we were given enough information to find these four probabilities over here. And in the denominator, we take the sum of the probabilities along all paths that go to B. So with this tree, it would be the product of the probabilities along this path plus the product of the probabilities along this path over here. Okay, so now let's apply this. So here's an example, somewhat a realistic example, at least in terms of evaluating tests, various medical tests. So suppose we know that approximately 0.4% of the people in the United States are living with an HIV infection, and modern HIV testing is known to be highly accurate in the following way. HIV screening detects 99.7% of people who have the infection and shows negative results for 98.5% of the people who do not have the infection. Now, just because the screening detects 99.7% of the people who have it, that doesn't mean that if you test positive, you have it. Okay, the probability for that is what we're looking for and could be quite different from 99.7. So that's our goal here is, suppose a person tests positive, what's the probability they actually have the HIV infection? So we'll do this first using the set theory form of Bayes' theorem, and then we'll explain it using a tree. All right, so we're given that the probability of an HIV infection for a person selected at random in the United States is 0.4%. We'll identify events. A1, the event an individual has HIV. A2 is the complement, the event the individual does not have HIV. And let's let B be the event that there is a positive HIV test results. So we're given this probability. Probability of A1, 0.004. That's this percentage expressed as a decimal. Probability of A2, 1 minus 0.004. We get 0.996. The probability of B given A1. So this is the probability a person tests positive given they have the HIV infection, 0.997. That was given. The probability of B given A2. Now we were given the probability that a person who does not have the test negative, but here we want the probability that a person tests positive given they do not have the infection. So this is going to be 1 minus the 0.985 that we were given. All right, so we'd like to find the probability A1 given B. Okay, so that's the probability a person has the HIV infection given they tested positive. So this first fraction is what you get when you express the conditional using the definition. And then we could express the numerator in terms of a conditional. So it's probability of B given A1 times the probability of A1. And we can break down the probability of B in terms of these two pieces. And you could see these are the two pieces that we get using this conditional probability idea. All right, so now once we have it in the form of Bayes' theorem, we can substitute in the values that we found up here. The probability of B given A1 is right here, 0.997 times the probability of A1, 0.004. You see this term also appears in the denominator. It's the first term here. And then we have to add probability of B given A2 times the probability of A2. So that's 0.015 times 0.996. And we get our final probability, 0.21. So you could see there's quite a difference. Person tests positive, but the probability that they actually have the HIV infection is 0.21. We could express this on a tree. So here we have the probability a person has the HIV, 0.004, right? That's our probability of A1. The probability they do not, 0.996. Okay, and then we have these other conditional probabilities over here. So as we said before, to calculate the probability A1 given B, right? This is the probability a person has the infection given they tested positive. We take the product of the probabilities on branches leading to B that pass through A1. So that would be this branch here. So we get 0.004 times 0.997. That's our numerator. The denominator is the sum of branch products leading to B. So I would want the products, right, along this branch. And then there's a second branch here. We have this branch goes to A2 and then to B. So I want the sum of those products. So I get this term here. And then along here I get 0.996 times 0.015. So we get the 0.21 once again. Okay, so that's the first example. In the second example, we consider a company that produces, let's say, 1,000 refrigerators a week at 3 different plants. Plant A produces 350, B produces 250, and C produces 400. Records show that A produces 5% defects, B 3% defects, and C 7% defects. Now suppose all refrigerators are shipped to a central warehouse, and then a refrigerator is selected at random from the warehouse and found defective. What's the probability it came from plant A? All right, so what do we want to find? Okay, well, we want to find the probability that a refrigerator from a given that it's defective. Okay, well, let's say this in other terms. We want to find the probability a refrigerator came from A given that we know it's defective, right? We know the probability that the refrigerator just comes from A is 350 over 1,000. Okay, so that probability is easy to find, but we want to know here the conditional probability. What's the probability it came from A given it's defective? All right, so we'll find that in a minute. Give the expanded form of Bayes' theorem needed for the solution. So here you could see this expanded form. Notice now we have 3 different sets that we're working with. Okay, so the probability the refrigerator comes from A given it's defective, the probability it's defective given it comes from A times the probability of A over this sum. So we could start substituting in values. The probability that the refrigerator is defective given it comes from A, that's our 0.05 term, and the probability it comes from A, that's the 350 over 1,000, or 0.35. So we get this very same term down here. Now this second term in the denominator, the probability of a defect given it comes from B, well, we know B makes 3% defects. And the probability a refrigerator comes from B, that's the 250 over 1,000. So that's where we get 0.25. And similarly, we could get this last term, 0.40 times 0.07. So when we multiply out and simplify, we end up with a probability of approximately 0.33. Okay, how does this look on a probability tree? Well, now I have my sample space can be divided up. If I think about producing a refrigerator, the refrigerators can either come from A, B, or C. These are the probabilities. And each plant has their own defect distribution. So to find the probability a refrigerator comes from A given it's defective, I have to multiply probabilities on paths that go through A and end up at D. So that would be this path here, 0.35 times 0.05. And then divide by the sum of all branch products for all paths that go to D. So I would have this path that goes to B and then D, and the path that goes to C and then D. So you could see we could pull these values right off the tree. 0.35 times 0.05 here and here, 0.25 times 0.03 here, and then 0.40 times 0.07. So we work this out, simplify, we get 0.33. Okay, and in our last example, let's imagine we have a certain company, 40% of the employees are females, and let's say that 60% of the male workers are married and 40% of the female workers are married. So we want to find the probability that a married worker is a male. So this is, notice, a conditional probability. We have a condition that a person is married. So we want to find the probability that they're male given that they're married, and then express this in terms of a tree. So let's let F denote the event that an employee is a female, and B the event that an employee is married. So we'll calculate our denominator first, the probability of being married. we break this up into these two pieces. So this is the probability they're married, given that they're a female, times the probability of a female. And this is the probability that they're married, given that they're not a female, or you could just say male, times the probability of a male. So we get this 0.4 times 0.4 plus 0.6 times 0.6. So 0.16 plus 0.36 adds up to 0.52. So that will be our denominator. And we want to find the probability that a person is a male, given that they're married. Okay, so again, we go back to the probability of male. Take that back. We go back to the probability of married, given that they're male, times the probability of a male, 0.6 times 0.6 over 0.52. So we get 0.692. On a probability tree, we could break this up in terms of females and males, the way you see over here, and then married and single. So females, we're using F. For male, we're using F complement. For married, we're using B. Let's say for single, B complement. So we want to find the probability of a male, given that they're married. So the product of probabilities of pass through the male side, okay, or the complement of females. So we go down here and then down here. So that gives us our numerator 0.6 times 0.6. And then in the denominator, we have the sum of probabilities along all paths that go to B. So we have 0.4 times 0.4 here, plus 0.6 times 0.6. And we get our result, 0.692. So this is the end of the video. Thank you for watching.